Okay, we're going to talk about another way to do this overall reaction, going from a carbonyl compound to an alkylated carbonyl compound. Now, we said the problem is we simply don't have, in the early days of chemistry, we didn't have a lot of strong bases. In fact, we didn't have any strong bases that can effectively deprotonate, fully deprotonate this alpha carbon. So one way to look at that is we need a stronger base. Another way to look at that is there a way to make this alpha proton more acidic? And as it turns out, the products of an earlier reaction, the Claisen condensation, allow us to do this. So this is a beta-keto ester. This beta-keto ester is made by the Claisen condensation. And this alpha hydrogen, instead of having a pKa, so up here at the top, the pKa of this proton is about 20. The pKa of this proton is maybe around, 11 or 12. So these alpha hydrogens, because they're between these two carbonyls, are extremely acidic. Sometimes people call these stabilized enolates or active methylene compounds. And so we can, using a very simple and available base, and when I say simple, I mean even people around 1900 had access to sodium methoxide. We can really easily, whoops, that's supposed to be O- on the oxygen. We can very easily and effectively and completely make this enolate. So this is kind of nice because our problem is we can't make our enolate. And now we can make our enolate very easily with a really routine base if we start with this beta-keto ester. So what are we going to do with this beta-keto ester? Well, let's treat this with an alkyl halide. This is a nice nucleophilic enolate, and it can do an SN2 reaction, and we typically want to make sure it's a primary halide, so we don't go into any E2 type chemistry. And I tell you what, I'm going to switch this around. I'm going to draw the ester going down, and I'm going to put the alkyl group coming off the side. Now, this clearly looks like our desired product. Whoa, what was that? Okay. Clearly looks like our desired product. But we have this crazy thing on here. Okay, our goal wasn't to make this alkylated beta-keto ester. Our goal was to make an alkylated ketone. So we have a fix for this. So in the third step, what we'll do is we'll treat this with acid and water. What does acid and water do to esters? Well, acid and water causes a hydrolysis reaction. And now we form something called a beta-keto acid, converted our ester to an acid. So this is alpha beta, thinking about the ketone in the beta position. And as it turns out, if you do this reaction in heat, this hydrolysis reaction, yes, you form the beta-keto acid, but under the heat conditions, it loses carbon dioxide, CO2. So that whole group it hydrolyzes and then falls off. And so this is called a decarboxylation. In your body, when you breathe out CO2 because you are doing decarboxylation reactions that are almost exactly like this. So this is a decarboxylation. And we form a product that, ta-da, is just like what we wanted to make up top. Now, we didn't start with the same ketone, but as long as we can make beta-keto esters, and the Claisen condensation makes beta-keto esters very readily, we can get access to alkylated ketones. So this is actually a really nice solution to the problem of I can't make an enolate. Well, then make a more stable enolate, and then you can use a weaker base to form it, and then you can go through all the chemistries. It's a really elegant solution. This is one reason why we learn about the Claisen condensation, because historically it gave people access to molecules like this, alkylated ketones.